everyone. I'm happy to be here this morning. I will present you some of the results we've had with a previous project we had sponsored by ESA, which was called Swarm and 4D-Earth core. And there is an extension of this consortium with the 4D-Earth Plus project that gathers efforts by people from DTU, Leeds, Paris, and Grenoble. So you are now aware that there's an increasing constraints on the variation of the magnetic field originating from the core. I give here one map of one time series of the secular variation, the rate of change of the field in Kourou in French Guiana. So you see these rapid changes, interannual changes. This is at the surface of the Earth, and when using Swarm, MSS, and other satellite data, we can build field models down to the core mantle boundary. And when we look at the rapid variation, this is nanotesla period, that's the secular variation filtered in time. You can see as a function of time and longitude here, it is at the core equator, that you have these oscillating patterns, some westward propagation, eventually some eastward propagation as well on various length scales. This is all, of course, dependent on the finite resolution we have for these changes at the surface of the core. But there's a lot of information to chew in order to try to understand the physics below the core surface. So from this variation of the field, we have discovered the presence of waves. So these are hydromagnetic waves. It is motion of the fluid, but also perturbation of the magnetic field inside the core. These are called QG-MC. QG is for quasi-geostrophic. That means much influenced by the rotation of the Earth by the Coriolis force. And MC, the M is magnetic. That means the restoring force is not only the Coriolis force, but as well the magnetic field in the magnetic force in the core. We see the westward propagation of patterns here. This is at the core equator again over more than 20 years. This oscillating pattern at a period of 6 years were first discovered from satellite data, but an reanalysis of a longer series, including ground station, have shown that we have actually very similar patterns. If we look at 6 years, this is extracted essentially from satellite data, and this pattern here is on 12-year period. Also includes longer satellite ground-based series. So there were no reason for the 6-year signal to be a single isolated wave in the core. There is a good reason to think that these waves populate the spectrum of the magnetic field also on longer time scales. We now have some evidence for decadal changes, and Julien was mentioning potentially pluridecadal periods for similar waves yesterday. So we can also use a numerical simulation to make some dissection of the physics. We are now in a position where, with assumptions about the turbulence in the core, in this simulation, in what we call large eddy simulation, we parameterize turbulence, it is possible to generate simulations that are at Earth-like condition. This is one example of such simulation with fluid motion in red and blue, magnetic field in brown and purple. And using this simulation, we can isolate several things that we can witness or not with the observation. One of them is, for instance, the appearance of a thermal or buoyancy plume near the ICB that will generate what we call QG alpha waves. So QG, that's Z invariant because of Coriolis, and alpha because magnetic force is the one that is important. And as they move outward, these waves, they morph into QG-MC wave, magneto-Coriolis. That means the Coriolis force enters the problem while the wave gets closer to the core equator. And this becomes much elongated in the phi direction. And this is these waves that we have witnessed, the second one, the QG alpha wave. We have not yet found them directly from magnetic data. I must stress that the speed of this wave is much faster than the fluid velocity. The fluid perturbation here is 5, maybe at most 10 kilometers per year, the outward propagation and westward propagation, we speak here about 1,000 kilometers per year. So that's 100 times bigger. So what should we expect from the core as a signal with the future mission we will have at hand? So if we look at the combination of MSS, Swarm, NanoMaxSat, we hope to have a longer time series, of course, because we have the data accumulate, but also we hope to improve the time resolution because of the low inclination mission. And we can look in simulation what we could expect. So this spectrum here is taken from the latest simulation by Julien at Earth-like condition. This is the spectrum of the secular acceleration, so the second time derivative of the magnetic field. And this is for several harmonic degrees, all normalized so that they have the same power here for comparison. You see that all these spectra for all the degrees, they superimpose, which is somewhat surprising. That means the decay in the power spectrum here does not really depend on the length scale we're looking at. What we have witnessed in QG MC waves is somewhere here between a couple of years and some 10, 20 years, okay? The spectrum is becoming smaller and smaller, so it will be more and more difficult to find the signal. But you see that happen some resonances at periods that are close to, close to 1 year. There is no relation with the Earth's orbit. But on periods close to 1 year, we have QG alpha waves there. We have not witnessed them yet, but if we are able to push the resolution towards the right here, there might be a possibility to detect these things and also to better dissociate using this kind of information about the spectrum for the magnetic field to better dissociate what's coming from the core from what's coming from outside the core, which could be induced signals that would be hiding somewhere here, the core signal. And of course, the mantle will filter the very short time scale here because of the screening. So these waves, why are they interesting? There are several things we are interested in with these waves. One of them is the coupling with the mantle and with the inner core. The fluid motion in the core, they can move in average east or west. And if there is a coupling with the mantle, this will generate changes in the length of day, changes in the speed rotation of the Earth because of angular momentum conservation. On subdecadal period, there are several spectral lines that have been isolated in the length of day that generate this kind of signals. So the observation is in red, and our prediction from a flow model inverted from magnetic data are in blue. So the overall fit is good given all the assumptions we do. The motions that are responsible for that are axially invariant, so these are zonal motion of that kind. And we have a bunch of waves, torsional waves and QGMC waves that could be that are candidates to explain this signal. And then the question is, what is the mechanism to couple the fluid to the mantle? So there are several candidates. One possibility is the electromagnetic coupling. A gravitational coupling involving the inner core is also possible. And the dominant torque might also depend on the frequency, depending on the properties of the deep Earth, like the viscosity of the inner core. So these waves are very interesting because they allow to probe properties of the deep Earth and to better understand how our planet is working as a whole. So some more detail about the mantle conductivity. This is a sketch taken from a paper by Stuart Russell. This is the core, this is the radius, and this is the mantle here. The conductivity of the core is usually much bigger than the conductivity of the mantle, okay? But very close to the core mantle boundary, there are some evidences that the conductivity should be relatively high because either the silicate are molten or because of changes of phases, and the proportion of iron is very badly constrained in this body. So you have ultra-low velocity zone here, imaged by seismologists, where the conductivity could be maybe 1/10 of that of the core. This is all debated. It is very difficult to sound the mantle conductivity when using induction from above, using the magnetosphere. You need long periods. I mean, people are working on that. Alexander Greiver is working on that. It is difficult because we need long time series and because of the ambiguity between the induced field and the core field. It is there are further ambiguities because the mantle will filter the high frequency signal, and we cannot exclude a strong conductivity here when using kinematic model like core flow inversion as we do. For this, we need a dynamical model that really couples the physics of the core to the electrical current in the mantle. So there has been actually only one study that did that, and it was based on the fact that the torsional waves, this is one family of waves we have isolated, that are illustrated here on this time radius, cylindrical radius diagram. You see things that move outward towards from the inner core towards the core equator, and you see there is very little reflection at the equator of the core. The property of this wave is such that the reflection property is governed in particular by the mantle conductivity, electrical conductivity. So this is what is designed here on this plot. This is a normalized measure of the mantle conductivity, and this is the reflection, the percentage of energy of the wave that is reflected. And you see that for certain value of the conductance, you have almost no reflection. So this study is with an axisymmetric background field. So it has to be generalized to a non-axisymmetric field, but there is some physics to chew here in order to understand the processes at work in the deep Earth. And the waves will help us to do that. Another geophysical observation of interest is the fact that the inner core is not static in the reference frame of the mantle. There is differential rotation. This has been found by seismologists who, for instance, look at repeating earthquake that come from in polar direction, that just sample the upper part of the inner core. And if you look at several earthquakes, sometimes you have the case of 3 events here where you superimpose events 1 and event 3. They superimpose very well, whereas event 2 and 3 and 1 and 2, they do not superimpose. And this can be explained by in two ways. Either you change the shape of the inner core, or you change you rotate the inner core. The inner core is electromagnetically coupled to the fluid. So the dynamics in the core will change the rotation of the inner core. There is no doubt about that. But the inner core is also potentially gravitationally coupled to the mantle. So there is some physics to understand here, and to know in which aspect the fluid motion can entrain the inner core is of interest, with potentially consequences in our estimation of the inner core viscosity. This has to be further investigated. One thing that is interesting with the waves is that when you have a wave, you have information on the medium that it goes through. In our case, it's magnetocoriolis waves, so it will sense the dynamo field. The dynamo field, we cannot measure it. What we measure is the potential field down to the CMB. But once you enter the core, there are electrical current. You cannot use the potential field approximation, and you need physics, okay? And these waves, the more wave we can see, the better will be the constraint on the dynamo field inside the core from observation. So there is a lot of science to be done here. This is one example from linear simulations by Olivier Barrois and Julien Aubert, where you see the fluid motion here as a function of time and longitude, and the magnetic signal associated with that. So these are linear waves that are numerically solved. There is a lot of information to be gained, but there is also a lot of work to be done, because we don't know the null space of this problem. So there might be many models of the field inside the core that would be able to fit this kind of observation. And there is also some work to be done to isolate how, the mechanism of the filter of the magnetic signal through the boundary layer inside the dynamo. With this project that is there for now 2 years, we will propose a benchmark of the several inversion methods for the reconstruction of the core dynamics from magnetic observation. So I have listed here a non-exhaustive list of possible tools that you can use stochastic models anchored to dynamo. You can use dynamo-based inferences. You can use machine learning methods. You can You can also learn using dynamo series with neural network. You could project onto eigenmodes. There are several ways of doing that. There is an eigensolver developed by Felix Gehrig in the 4D Plus team, which take benefit of both the, I mean, if we're able to calculate eigenmodes in somewhat realistic condition, the benefit here is that you couple the spatial structure of the mode with its temporal structure. So it would be maybe a way to improve the constraints on our recoveries. I give here one example of these eigenmodes. So this is the flow, so the east-west flow in red-blue, and this is the associated magnetic perturbation. So of course the observation won't tell us in all these details, and it might be even more complicated as the background field gets more complex. But we have no eigensolver able to show this kind of pattern. So stay tuned. We will launch a benchmark in the coming months. So I conclude now. I think it's time for everyone to go to lunch. With a longer coverage from space, we hope we can have a tighter constraint indirectly of the geophysics of the deep Earth. We can use these waves in many aspects to sense the dynamo field, the electromagnetic properties of the deep mantle in link with seismic observations. And we will propose a benchmarking exercise on the core flow inversions. And I stop there. Thank you.